Today we're going to talk about rational functions and their asymptotes. So let's first define this. A rational function can be written in the form f of x equals p of x over q of x, where p of x and q of x are polynomials, and q of x obviously cannot be 0. So just remember, rational has the word ratio in it. Ratio means fraction. So rational functions. Let's look at a couple. What if I asked you to graph f of x equals 1 over x minus 2? Now you should be familiar with what 1 over x looks like. And so this is just going to be a shift of 2 units to the right. So instead of, let's draw 1 over x. Okay. If I shift this 2 units to the right, now I have an asymptote instead of the y-axis, which would be x equals 0. Now I have an asymptote at x equals 2. And so the domain of this function is all real numbers except 2. And the range is going to be also all real numbers, except it never crosses the x-axis, so y is never equal to 0. Alright, so that asymptote at x equal 2, notice that's what makes the denominator 0. And so that's what we want to investigate today. What if I had a more complicated function? How about 2x squared over x squared minus 1? Well, let's use a calculator to get us a quick picture of this. And we got 2x squared divided by, use parentheses, x squared minus 1. All right, and graph. Now notice here, it looks like as x gets really big positively, as x goes to infinity, let's hit trace. As x is going out there, look at my y values, they're getting, looks like maybe closer and closer to y equal 2. It seems like maybe y equal 2 is a horizontal asymptote. What if I jump to the other side? What if x is going to negative infinity? Seems like the same thing. Now, this obviously is pretty crude estimation, but at least it's giving us an idea that there's some horizontal asymptote. There's some value, some y value that this is approaching as x approaches negative infinity or x approaches positive infinity. And then it also looks like we have some issues around x equals negative 1 and x equal positive 1. And it turns out that sure enough, look at my y values as, let's see, negative 1.0001. The y values are skyrocketing as x approaches negative 1 from the left side. And so it looks like as x approaches negative 1 from the left, our function is going to positive infinity. And as x is approaching negative 1 from the right, our function is approaching negative infinity. And then the same thing over on the other side. As x approaches 1 from the left, that would be like 0.999, our function is also approaching negative infinity. And then if I'm approaching x equals positive 1 from the right, so like 1.01, 1.0001, it looks like our function is approaching positive infinity again. So to summarize, and this is just looking at this crudely, it looks like we have a horizontal asymptote at y equal 2, and then vertical asymptotes, we have 2 of those. It looks like at x equals negative 1 and at x equals positive 1. So that's what we want to do, is we want to analyze today how we can figure out where the asymptotes are for these rational functions. So let's start with vertical asymptotes. To find a vertical asymptote, you factor the numerator and denominator, if possible, and you cancel any common factors, and then look at the denominator, and any values that make the denominator 0 are going to be where your vertical asymptotes are. So let's look at an example. Let's find the vertical asymptotes for this function. And here you might want to hit pause just to try and factor and cancel yourself. All right, in the numerator, it's going to be an x minus 5x plus 3. All that practice with factoring in algebra 1 and 2 come into play now. And then in the denominator, x plus 4, x plus 3. So we do have common factors, x plus 3's, those cancel. And so now I'm looking at the denominator, and if x were equal to negative 4, that's going to cause a divide by 0. That's going to be a vertical asymptote. So this graph will have one vertical asymptote, and that's at the vertical line x equals negative 4. So let's go ahead and take a look at this graph on the calculator. So we have, put it in parentheses, x squared minus 2x minus 15 divided by, and then the denominator, what was that, x squared plus 7x plus 12, I think, right? Yeah. And typed it incorrectly, so let's hit graph. Okay, and so you can see that it looks like at x equals negative 4, we're going to have a vertical asymptote there. Now, what about the factor that we canceled? What about that x plus 3 factor? What happens when x equals negative 3? Well, if I hit trace and I type in negative 3, you can see that y is undefined. This function's undefined there, because the original function included the x plus 3 in the denominator, so we know that for the domain, x cannot equal negative 4 or negative 3. But we don't have a vertical asymptote at negative 3, and that was one of the factors that canceled. So what's happening at negative 3? Well, let's see what happens if I go a little bit to the right. I'm at about negative 7.02. What if I go the other way? Negative 10, negative 8.2. Let's zero in. How about negative 3.00001? Looks like I'm about negative 8. How about negative 2.9999? So it looks like maybe where that hole is at is going to be negative 3, negative 8. So let's switch to a different color. So at x equals negative 3, there's a hole in the graph. And the coordinates of that hole is negative 3 comma negative 8. And how could I have figured that out without using the calculator? Well, look at what's left here. After I cancel that x plus 3 factor, I have a new function, g of x, which is equal to x minus 5 over x plus 4. That's exactly the same function as f of x, except g of x doesn't have a hole at negative 3. F of x does. G of x is fine for negative 3. And so if I evaluate g of negative 3, I get negative 3 minus 5, which is negative 8, over negative 3 plus 4, which is 1. So negative 8 over 1 is negative 8. And so that's how I know exactly where the hole is in this original rational function f of x. So it turns out we found two things here. We can find vertical asymptotes by factoring the numerator and denominator, canceling any common factors, and whatever makes the denominator 0 is going to be a vertical asymptote. And any factors that cancel represent holes in the graph. All right, so let's talk about horizontal asymptotes. If I want to find a horizontal asymptote, I need to consider this. And this is new notation, but that represents the limit as x approaches infinity of p of x over q of x. What is that? Let me circle this. What does this thing mean? That just means what's happening to my function as x gets bigger and bigger and bigger and bigger. And then we could also consider negative infinity. So, there's three possibilities. We need to look at the degree of p of x and the degree of q of x. That means the highest power of your variable in the numerator and the denominator. Now, if the degree in the numerator, the p of x, is greater than the degree in the denominator, for example, let's say we had an x cubed plus 2x, blah, 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 and in the denominator we had an x squared minus 7x, plus 4, whatever. Okay, that's an example where the degree in the numerator is greater than the degree in the denominator. Okay, when that happens, it turns out that this limit is going to equal positive or negative infinity, and so there's no horizontal asymptote. All right, what's another possibility? Well, how about if we switch it? What if the degree in the numerator, the p of x, is going to be less than the degree in the denominator? So for example, if I had, let's say, an x to the fourth, let's say a 3x to the fourth minus 3x cubed plus x squared, blah, blah, blah. And then in the denominator I had maybe a 2x to the fifth minus x to the fourth, etc. Now the degree is greater in the denominator, and so when that happens, the limit winds up equaling 0, and so the horizontal asymptote is the x-axis, y equals 0. Probably write x-axis in parentheses. Okay. All right, and so this should make sense because if the degree in the denominator is bigger than the degree in the numerator, as x gets really big, like 1 million, 10 million, 1 billion, 1 trillion, raising that to the 5th power is going to make the number so much bigger in the denominator than in the numerator that your fraction's getting smaller and smaller and smaller and closer to 0. And then likewise for the first case, if the degree is higher on top, then the numerator is getting so much bigger than the denominator that your values for f of x are going up and up and up and up. Now, so there's one last case. What if the degrees are equal? What if the degree in the numerator and the denominator are the same? For example, let's say we had 7x squared minus 4x plus 1 and 3x squared plus x minus 9. Just made those up. So what's going to happen in that case? Well, it turns out that the limit is going to wind up equaling the ratio of the coefficients of the highest degree terms. And so what do I mean by that? We'll find, and by the way, they might not always be in descending order. So you have to look at the highest power of x, wherever it is. So in this case, we have 7. And in the denominator, the highest degree term has a coefficient of 3. And so the limit is going to equal 7 over 3. And so it turns out that that's the horizontal asymptote. So in this case, your horizontal asymptote would be y equals 7/3. All right. Let me jump back for a minute and look at these problems we did earlier. So in this first case, we have the degree is bigger in the denominator. We have x to the first. We don't have an x in the numerator. So that limit is 0. So then we have an asymptote at y equals 0. And sure enough, there's your horizontal asymptote. In the second case, the degrees were the same. And so it's the ratio of the coefficients, which would be 2 over 1. And that was our horizontal asymptote, y equal 2. All right, so now you try one, and it's a good idea to hit pause and give it a shot. Find any vertical or horizontal asymptotes for this function. All right, let's start with the horizontal asymptotes because that'll be quicker. All right, so we look at the degree in the numerator and the denominator, and the degree is 2. So the degree is the same, so it's going to be the ratio of the coefficients of those terms, which means we have a horizontal asymptote at y equals 1/2. All right, now let's look for the vertical asymptotes. So for vertical asymptotes, we need to factor this. So I can factor an x in the numerator, and I'm left with x minus 4. In the denominator, I can factor out a 2, and then I'm left with x squared minus 4, which I can further factor. That's the difference of two squares. X squared minus 4 is x plus 2, x minus 2. So now notice there's no factors that cancel, so there's no holes in the graph. Maybe we want to write that. There's no holes in the graph. But we do have vertical asymptotes, and that would be what makes this 0. That would be when x is equal to negative 2. And what makes that 0? That would be when x equals positive 2. So those are your vertical asymptotes. X equals negative 2, and x equals positive 2. So let's just call this up on the calculator and graph it. Although we could do a crude sketch by hand if we really needed to. X squared minus 4x divided by 2x squared minus 8. Make sure we typed it in there correctly, looks good, and graph. And sure enough, let's start with the vertical asymptotes. We have one at x equals negative 2, x equal positive 2. And then the horizontal asymptote, y equal 1/2. And actually, let me graph y equal 1/2 for you. Y equals 0.5. And let's change the color of that. Let's make that red. Somewhere. Oh, yellow would be nice. Did I miss red? There it is. Okay, graph. And sure enough, that looks pretty convincing that that's our horizontal asymptote. Right, so now with those few simple tools, you can find all the asymptotes and holes in a graph, and you should be able to get a pretty good idea of what your graph looks like without even using technology. All right, let's try another one. Find all the asymptotes and holes in this graph. All right, let's start with horizontal. So horizontal asymptotes, what do we got? Well, we look at our degrees. The highest degree in the numerator is a squared, and the denominator is a cubed. It's bigger in the denominator, so that means that limit is equal to 0. So the x-axis, or y equals 0, is a horizontal asymptote. Okay, step 2. Let's find vertical asymptotes. We're going to factor. So x squared minus 4 is an x plus 2, x minus 2. In the denominator, I'm going to factor by grouping. So the first two terms, I could factor out an x squared, and I'm left with x minus 2. Oh, there's a hole in the graph. And then in the second one, I'm going to factor out a negative 9, and I'm left with x minus 2. Now I can further factor this. I have an x minus 2 in both of those, and then I have an x squared minus 9. And then the x squared minus 9 I can further factor to be x plus 3, x minus 3. Alright, so let's put the simplified answer here. Boom. Alright, let's cancel any common factors. X minus 2. So that means we have a hole in the graph at x equals positive 2. Because positive 2 here would make that 0. And I can actually find the coordinates of that. It's going to be at 2, comma. Now if I plug in 2 to my function after those are canceled, I'm going to get 2 plus 2 in the numerator. In the denominator, 2 plus 3 is 5. 2 minus 3 is negative 1. So I'm going to get negative 4/5. So that's exactly where the hole is at in my graph. Alright, so let's go back here, vertical asymptotes. So in the denominator I have an x plus 3, so if x is equal to negative 3, there's a vertical asymptote. And then for the other factor, if x is equal to positive 3, That would make that 0, and so there's another vertical asymptote. So there's all the information about that rational function. So, just as a summary, the line x equal a is a vertical asymptote of the graph of f when f of x approaches infinity or negative infinity as x approaches a, either from the right or from the left. And the line y equal b is a horizontal asymptote of the graph of f when f of x approaches b as x approaches positive or negative infinity. And so sometimes, it helps to read these math definitions and theorems a few times. So read it over again. Everything that's in there is really important. If there wasn't, it wouldn't be in there. So you can't just take out pieces. So read through each of those, a couple of times and make sure you really get a visual understanding of what it's saying. And then for your assignment, it's section 2.6 and it starts on page 147.